Okay. Well, people have had some time to get here, so I'm just gonna get started. Chapter 15 homework is due on the 17th. The chapter 19 homework is due on the 24th. The chapter 15 quiz will be an SI today. And yeah. Oh, I need to actually plug this in before. So we're starting the atmosphere. I went over the learning goals. The format will go over the constituents of the atmosphere, the divisions of the atmosphere, properties and functions of ozone in the atmosphere, the distribution of insolation on the Earth from the sun, the greenhouse effect, the latent heat of evaporation and condensation, heat conduction on Earth's surface, air pressure, how it's measured, the fundamental atmospheric measurements, the differences between absolute humidity and relative humidity, the data that goes into the heat index, and the dew point and how it relates to precipitation. We'll talk about how a psychrometer measures relative humidity. We'll go over psychrometer tables. We'll describe what causes wind and air currents. We'll describe isobars and the general movement of air between different isobars, land and sea breezes, and the Coriolis force and how it affects the rotation of waves. And we'll differentiate between cyclones and anticyclones. We'll describe jet streams. We'll look at the differences between the four cloud types and talk about how clouds form. So the atmosphere is the gaseous shell or envelope of air that surrounds the Earth. That's what I forgot to do. Oh well. That we need to breathe and live in. We watched that video last week. I mean on Monday, so I'm going to skip it. So, meteorology is the term commonly applied to the study of the lower atmosphere. In the past, it was used to describe everything above you, which is again why meteors are called meteors, and it's also called meteorology. It's because they were both talking about things in the sky, but not stars, kind of. More generally describe the entire atmosphere. And the conditions of the lower atmosphere, what we call the weather. Oh, what did I just do? Something very wrong just happened. Well, let me quickly mark you in by. And then I will get back. Yes. So when we talk about the conditions of the lower, when we talk about weather, that's the conditions of the lowest part of the atmosphere. Weather happens in the bottom layer of the atmosphere. And we're going to talk about the composition of the atmosphere, its properties, and various mechanisms. So our atmosphere is a mixture of various gases. With various amounts, holds varying amounts of suspended liquid droplets and solid particles. Most of the atmosphere is made up of nitrogen and oxygen, about 99% by volume of air near the Earth. And both of these are diatomic, N2 and O2. Argon makes up about 1% of the atmosphere, and carbon dioxide is a little bit more than 0.03%. And these are the other major constituents of air. And very small quantities of many other gases are found in the atmosphere. So nitrogen is about 78%, oxygen is about 21%, argon is 0.9%, carbon dioxide is 0.03%, and then there's a small amount of other stuff. There are traces of neon, helium, methane, nitrous oxide, and hydrogen. And then some variable quantities of Water vapor is the one that varies a lot. It varies from about 0 to 4% of the air. Carbon monoxide is emitted by various things like cars and other combustion and stuff. Ammonia, and then there's solid particles like dust, pollen, etc. These are all around in the air. So carbon monoxide is largely the product of incomplete combustion in engines. So the main source of carbon monoxide is car engines. Various automobiles, things like this. Okay. Those are the main source of carbon monoxide. In general, though, the relative amounts of the various major atmospheric constituents remain more or less constant. Nitrogen, oxygen, and carbon dioxide are all involved in various life processes of plants and animals. And so under normal circumstances, they remain in a sort of balance. And these gases are constantly being extracted and replenished during various natural processes. Unfortunately, at the moment, we're adding more carbon dioxide to the atmosphere by burning stuff than natural processes can store away. So the carbon dioxide component is going up. So in a process called photosynthesis, plants will consume carbon dioxide and produce oxygen as a waste product. Animals, on the other hand, consume oxygen and produce CO2 as a waste gas. So, and then nitrogen is taken up in by some plants and released back into the atmosphere during organic decay. The nitrogen cycle is a lot more complicated. There are various single cell life forms involved and things like that. But oxygen and carbon dioxide, plants consume carbon dioxide, release oxygen. Animals consume oxygen, release carbon dioxide. And then nitrogen gets picked up by various processes and fed into plants, and then that's how it gets into animals. Certain plants can pull nitrogen from the environment. They didn't really do this with the help of certain single cell like bacteria. Now, due to the gravitational attraction between the Earth and the atmosphere is constantly being pulled down by the gravity of the Earth. The density of the air is greatest near the surface of the air. Basically, all the air is piled up on top of itself. It is squeezing the air below it. So the air at the bottom is the densest. So, and it's a pretty dramatic change. Over half the atmospheric mass lies below an altitude of 11 kilometers, 7 miles. So if you go up only 7 miles, half the atmosphere is below you by mass. And 99% lies below an altitude of 30 kilometers or 19 miles. But because of this gradual thinning, there's no clearly defined upper limit to the Earth's atmosphere. It just sort of peters off into space. And we can draw sort of an arbitrary line. There's an arbitrary line for what we've designated space. It's at 100 kilometers. Basically, the atmospheric concentrations become less and less, and it will simply merge with outer space. So the arbitrary line for I have gone to space is 100 kilometers. It has to do with certain factors to do with whether orbits are stable and such. that's the point where the atmosphere is thin enough that we consider it space. That is generally inside what is inside one of the generally considered layers of the atmosphere, the top layer of the atmosphere. We'll get to those, but that line for space is like near the bottom of the top layer of the atmosphere, actually. So there are several regions in the atmosphere. So various physical properties of the atmosphere do show distinct vertical divisions that vary with altitude. Density or pressure doesn't, it just gradually reduces until you hit space. But some of the things that do change are things like temperature. The way temperature changes as you go up through the atmosphere. So if you start at the ground, as you go up, it gets colder. But there's eventually a height where that reverses. It starts to warm as you go up, and then it reverses again and cools again, and then finally it reverses again and warms again. So, and there are also layers of ozone ion concentration. There's the ozone layer where there's a lot more ozone. We want our ozone high up in the atmosphere where it's blocking UV radiation and not down at the level of Earth where it's doing horrible damage to our cells, because ozone is nasty stuff. So, temperature-wise, so the most recognizable divisions within the atmosphere can be distinguished based on vertical temperature variations. This is how temperature changes as you rise. So, there are 4 different temperature regions. At the bottom, the one we are currently standing in is the troposphere. This is from the ground up to about 16 kilometers or 10 miles. This is where all the weather is, and where most of the atmosphere is. In the troposphere, temperature decreases with altitude. As you go up, it gets colder. That's what your intuitive experience with temperature. As you go higher up, it gets colder. The next layer is the stratosphere. This is from about 16 kilometers to 50 kilometers, from about 10 to 30 miles. The stratosphere, in the stratosphere, as you go up, it actually warms. That's because the ozone layer is in the stratosphere, and the ozone layer is absorbing energy from all that UV radiation that it's blocking. And so that's heating the top of the stratosphere, so it warms as you go up. Next, above the stratosphere is the mesosphere. Once again, as you go up, it gets colder. This is from about 30 to 50 miles. And then above that is the thermosphere, which goes from about 80 kilometers to outer space. You don't need to memorize the specific thicknesses, but you do need to be able to recognize them on like a graph. And you know, the official line for outer space is, well, depends where you are. There are 2. There's the American one, and then there's the international one. The international one's at 100 kilometers, which is in the thermosphere. The American one's at 50 miles, which is at the bottom of the thermosphere. So, the troposphere contains over 80% of the atmospheric mass and virtually all the clouds and moisture. The troposphere is the most complex and varying of the layers of the atmosphere. This is where all the mixing and movement and stuff occurs. The other layers are a lot more stable and less active. And most weather occurs in the lower parts of the troposphere. And within the troposphere, the temperature of the atmosphere decreases an average of about 6.5 degrees Celsius per kilometer as you go up with increasing altitude due to less air molecules capable of absorbing heat. The thing is, the troposphere, that layer, is primarily heated from below by the ground. The main source of heat for the troposphere is the Earth re-radiating the heat it absorbs from the sun. That's why it's warmer at the bottom. And the top of the troposphere has temperatures of about minus 45 degrees to minus 50 degrees Celsius. And those numbers are the minus 49 to minus 58 degrees Fahrenheit, doing the conversion in my head. But it's very cold Celsius or Fahrenheit. So the stratosphere and the troposphere together account for 99% of the atmospheric mass. So the stratosphere is the next layer up. In the stratosphere, the temperature increases. It's not as smooth as the decrease in the troposphere. It's in a non-uniform manner as you progress upwards through the stratosphere due to direct heating by the sun and the UV absorbed by the ozone in this region. The vast majority of the ozone layer is in the stratosphere. So there's much higher ozone concentration in the stratosphere, and this absorbs UV radiation from the sun. Above the stratosphere is the mesosphere, where again the temperature progressively decreases with altitude. There's basically barely any air molecules there. And above the mesosphere, Earth's atmosphere becomes exceedingly thin. And this is called the thermosphere, where it's intensely heated by the sun, and this results in an increase in temperature once again. And the thermosphere extends to the outer reaches of Earth's atmosphere. Continuous. So in the troposphere, temperature goes down. In the stratosphere, temperature goes up. In the mesosphere, temperature goes down. And then in the thermosphere, temperature goes up. Things like meteors and auroras happen in the meso and thermosphere. Well, mostly in the mesosphere, actually. The thermosphere, this is where you have things like the ISS. The International Space Station is in the thermosphere. And here at 100 kilometers is sort of the official international line for space. And you can see you can sort of extend the thermosphere up to 200. Another thing you can classify is ozone concentration. Certain parts of the atmosphere have more or less ozone. There is an area of the atmosphere with a lot of extra ozone. Ozone, which is O3, forms from the dissociation and recombining of molecular oxygen, O2. So basically, oxygen gets hit with energy from UV radiation. It splits, recombines to form O3. And when you have O3, that allows you, that O3 could also absorb, and then that O3, when it recombines to form O3 and it bumps into something, you can emit energy. Like, and this O3 forms most efficiently where there's the proper balance of UV radiation and oxygen molecules, which is at about 30 kilometers in altitude. So there's this region between about 15 to 50 kilometers in altitude that's characterized by an ozone concentration. This is the ozonosphere. This is in the very top of the troposphere and the stratosphere. So the ozone layer is mostly in the stratosphere. And the greatest concentration of ozone is roughly equivalent to the stratosphere. And this acts sort of as an umbrella to shield life on Earth from the most harmful UV solar radiation. So the absorption of UV radiation also explains the fact that the temperature in this region goes up. And near ground level, very little natural ozone is found, which is nice because it's pretty nasty stuff. It's a very potent oxidizer, so it will tear your cells apart, which makes it great for cleaning things. So if you have like a car or something that people smoked in, you could, or a room that people smoked in, you can seal it and put in an ozone generator, and the ozone will destroy all those terrible smelling molecules. But you really don't want to be in there because it'll destroy the useful molecules in your lungs as well. So near ground level, very little natural ozone is found. Yeah, ozone, if you spray a stream of ozone on like a glove, it'll just eat through the glove. You really don't want that to happen to your flesh. So here is a short video about ozone. Hopefully there won't be an ad. I need to go through and replace all these.
The Earth is...
Oops. Just a second. Oh, no. I forgot to change the sound setting. Oh, good.
The Earth is covered with a thin layer of gas we call the atmosphere. Atmospheric pressure decreases rapidly as we move away from the surface. In the region known as the stratosphere, far above the troposphere in which all our weather occurs, the atmosphere is very thin. Here, short wavelength, high-energy radiation from the sun causes dissociation of oxygen molecules. When short wavelength ultraviolet light strikes an O2 molecule, it dissociates into oxygen atoms. When an oxygen atom collides with an oxygen molecule, an ozone molecule, O3, may be formed. The O3 molecule that is formed has excess energy, the energy released when the oxygen atom combines with the oxygen molecule. If it does not get rid of that excess energy, it rapidly dissociates back into O2 and O. However, if the O3 molecule collides with any other species present, most likely an N2 molecule, it transfers the excess energy to this molecule and becomes stabilized. When solar radiation from the ultraviolet region of the spectrum strikes an ozone molecule, it may be absorbed, and the O3 molecule dissociates. The ozone cycle in the stratosphere involves formation of oxygen atoms and reaction of these with O2 to form O3. Stabilization of the newly formed O3 by energy transfer through collision, and dissociation of O3 by solar radiation. The ozone layer that is established in the stratosphere by these equilibria shields Earth's surface from the ultraviolet radiation that is harmful to living systems.
So, and here's a short video about the issue of ozone depletion, and how chlorofluorocarbons manage to damage the layer of the ozone and reduce the protection.
Funny. The man has jokes.
He's funny. Okay.
Okay.
15 to 35 kilometers above Earth's surface, a gas called ozone surrounds the planet. The ozone layer acts as a barrier between Earth and ultraviolet radiation from the sun. However, pollution has caused the ozone layer to thin, exposing life on Earth to dangerous radiation. Earth's atmosphere is made up of 6 layers. The second layer, called the stratosphere, contains the ozone layer. The ozone layer is made up of a highly reactive molecule called ozone, which contains 3 oxygen atoms. Ozone is a trace gas in the atmosphere. There are only about 3 molecules for every 10 million molecules of air. But it does a very important job. The ozone layer acts as Earth's sunscreen, absorbing about 98% of damaging ultraviolet or UV light. But the ozone layer has gotten thinner. Chemicals called chlorofluorocarbons, or CFCs, are the primary culprits in ozone layer breakdown. A CFC is a molecule that contains the elements carbon, chlorine, and fluorine. CFCs are mostly found in refrigerants, aerosols, and plastic products. When CFCs are exposed to ultraviolet rays in the atmosphere, they break down into substances that include chlorine. The chlorine reacts with the oxygen atoms in ozone and rips apart the ozone molecule. Areas of damage in the ozone layer are often called ozone holes, but that name is misleading. Ozone layer damage is more like a thin patch, with the thinnest areas near the poles. The ozone layer above the Antarctic, in particular, has been impacted by pollution since the mid-1980s. There, the region's low temperatures speed up the conversion of CFCs to ozone-damaging chlorine. About 90% of CFCs currently in the atmosphere were emitted by industrialized countries in the Northern Hemisphere. In 1989, the Montreal Protocol banned the production of ozone-depleting substances. Since then, the amount of chlorine and other ozone-depleting elements in the atmosphere have been falling. Scientists estimate that chlorine levels will return to their natural state in about 50 years. By then, the Antarctic ozone hole will shrink to smaller than 8 million square miles.
And this has been observed. Our ozone hole has been shrinking. It's actually turns around and it's getting smaller. And one of the nice things about, this is sort of that proof that if everybody gets together and agrees to do something about a big problem like this, you can actually do it, which is a good sign for the other big problem we have, which is the increase in greenhouse gases. So another layer that we can talk about in the atmosphere is the ionosphere. The ionosphere is a layer region between about 70 and several hundred kilometers in altitude, which is characterized by a very high concentration of ions. And there isn't really one layer there. There's several layers that each are labeled. The subregions are labeled the D, E, and F layers. And the thing is, these ions, they're charged particles, so they can interact with electromagnetic waves. You can bounce radio waves off them. And this is how shortwave radio can go all the way around the world, and why AM radio will have really long ranges at times compared to FM, because AM radio will actually bounce off the ionosphere and FM won't. So you can bounce off the ionosphere. You can bounce various radio waves off these various layers of the ionosphere. And before satellites were available, the D, E, and F ion layers were used to provide global radio communication via the reflection of very specific frequencies. And you can still do this if you get into ham radio or something. And these are high up. These are up in the mesosphere and the thermosphere, because they're fed by material emitted by the sun and captured in Earth's magnetic field. So these are, actually they're up all in the thermosphere, basically. But you can bounce radio waves off them, and they vary in strength. So whether you have long range or not depends. They vary day and night, things like that. So here's a short video about the ionosphere.
Hey, I'm Mr. Weather. Did you know there's a non-distinct atmospheric layer? It's called the ionosphere, and it's a series of regions in parts of the mesosphere and thermosphere, where high-energy radiation from the sun knocks electrons loose from their parent atoms and molecules. The electrically charged atoms that are formed are called ions. There are three main regions of the ionosphere that fall in the upper part of the mesosphere and lower parts of the thermosphere. We have used the ionosphere to boost radio communications in the past before satellites became common. Radio operators would bounce the signals off the sky to extend their range. The ionosphere changes daily and seasonally. These changes can impact radio transmissions and communications as well as GPS. Scientists monitor the ionosphere so radio operators can anticipate disruptions. Watch each week to learn more.
And there are also effects from solar activity on the ionosphere. So that's, you know, how active the solar wind is and stuff can affect it as well. So here is sort of an example. You can bounce radio waves off ion layers, or you can also send them up to satellites and transmit them off of them. This is showing just bouncing it off a satellite, which is something we have done. There are several satellites that were launched that were just reflective balls, that were designed just that you literally just bounced radio waves off of them. Some of the early ones, but these days generally satellites receive and transmit radio waves. Now the northern lights, or aurora borealis, are beautiful displays of lights that are generated in the upper atmosphere over high latitude areas. It's called the aurora borealis in the northern reaches. In the southern reaches, in the southern hemisphere, it's called the aurora australis, because borealis means north and australis means south. And so material from the solar wind, from solar disturbances, provides incoming energetic particles that supply energy for ions and electrons to recombine. And when these ions and electrons recombine, they emit visible light and other radiation. So when we get to the talking about the sun, we'll talk about the solar wind and solar weather and stuff. But that is one of the major drivers of the ionosphere and auroras. So this is a short video about the formation of auroras. It starts with the emission of material from the sun.
On Arctic nights, the aurora often flames across the winter sky. What is it, and where does it come from? This is where the tale of the aurora starts. On the sun, a star of average size among billions of other stars in our Milky Way. The sun acts as an enormous power plant. The energy is created deep inside the core of the sun. Here the temperature is over 14 million degrees, and the pressure so enormous that hydrogen atoms are squeezed together into another element, helium. This nuclear reaction releases energy. The light radiates outward from the core of the sun. In the outer layers, the heat moves to the surface in huge eddies called convection cells. These electrical currents of charged gas create magnetic fields inside the sun. In some places, strong magnetic fields push their way up through the surface. They slow down the eddies of hot gas. The surface cools, and darker sunspots appear. The electrically charged gas is called plasma. The plasma drags the magnetic field further outwards. The magnetic field stretches and twists like a rubber band, and then the rubber band breaks. Several billion tons of plasma is hurled out from the sun. This is called a solar storm. The solar storm can reach speeds over 8 million kilometers an hour. After 6 hours, it blows past the planet Mercury. After 12 hours, the planet Venus. And after 18 hours, the solar storm reaches Earth. When the solar storm reaches our planet, something strange happens. An invisible shield, the Earth's magnetic field, deflects the storm. The magnetic fields couple together and create a funnel where the gas streams down on the daylight side of the pole. This is the daylight aurora. The magnetic fields stretch further back and couple together. The magnetic rubber band breaks, and gas from the solar storm streams along the magnetic lines towards the poles on the night side. This is the nighttime aurora.
So here's the Aurora Borealis, it's seen in a Denali National Park in Alaska. Normally you have to go pretty far north or south to see the auroras. Though on particularly intense solar storms, you can see them as far south as here. There was one a little while ago where we were supposed to be able to see it. I didn't actually manage to, but now let's talk about the energy in the atmosphere. The most important energy source for the Earth and its atmosphere is the sun. The main thing that heats the atmosphere is the sun. The sun's about 93 million miles from the Earth, and though it emits a vast amount of energy, that energy goes in every direction. So only a very small amount of that energy actually hits the Earth because, well, it's a sphere 93 million miles in radius with the Earth as a little speck on it. The portion of solar energy that's incident on the Earth's atmosphere is called insolation, incoming solar radiation. Yes, it's a really confusing name, but that is what it is called. So insolation is the energy coming from the sun. And due to the tilt of the Earth, the insolation from the sun is not evenly distributed over the Earth's surface. Because of the tilt of the sun, we get seasons. On Earth, And over time, the top of the Earth's atmosphere will receive a relatively constant amount of solar radiation, even though the sun's output might vary a little bit. Sun's output doesn't vary a lot. If the sun's output varied a lot, everything on Earth would die. So it's pretty stable. The surface of the Earth, however, only receives about half of the insolation. About half of it gets absorbed or reflected away. So if we look at the incoming solar radiation, about 7% is scattered away by the atmosphere, about 24% gets reflected by clouds, and another 2% gets reflected by the ground. That all together is what's known as the albedo, the amount that is reflected. And so if the albedo for Earth is about 33%, about a third of the light that hits the Earth gets reflected back. Venus, on the other hand, has an albedo of about 70%. It's why it's so bright in the sky, because about 70% of the light that hits it gets reflected back. So it's a very bright object. Of the incoming radiation, 15% just gets directly absorbed by the atmosphere. Another 2% gets absorbed by clouds. 5% is scattered by the atmosphere down to the ground where it will be absorbed. 23% goes directly to the ground, and 22% goes through the clouds to the ground. And this gets absorbed by the ground. So about 50% of the total insolation actually reaches the Earth's surface. And that gets absorbed. But that warms the Earth up. Anything with a temperature emits light. So you are emitting light right now because you have a temperature. And so the Earth will then re-radiate that as terrestrial radiation in the infrared. And that gets absorbed in the atmosphere by water vapor and carbon dioxide. And that's the primary thing that warms the lower atmosphere. So albedo is the amount of light that a body reflects. Of the insolation received by Earth, only about 33% is reflected back to space is returned to space via reflection and scattering. Therefore, the Earth has an albedo of about 33%. The moon, on the other hand, has an albedo of only 7%. It's actually pretty dark due to its dark surface and its lack of atmosphere. That's why you don't see the moon during the day very easily. Well, we see the moon because it's big and close, but it's not actually that light. And as viewed from space, the Earth is much brighter and much more impressive than the moon. If you see pictures of the Earth from space, it kind of looks like it's glowing, unlike the moon, comparatively. And then something like Venus has an albedo of about 70%, which is why it's so bright in the sky. Now, the exact brightness of Earth at any given time and place largely depends on the amount of cloud cover and the ratio of land to water. Land has a higher albedo than water. Clouds have a higher albedo than either of them because they're white, so they reflect a lot of light. That's why, if you're covered in clouds, you end up with a very high albedo usually. Now, most of the heating of the direct heating of the atmosphere comes from the Earth and not from the sun. In particular, the troposphere, the layer of the Earth that we live in, gets most of its energy content from the Earth. And the absorption of Earth's energy is accomplished predominantly in three ways. The Earth heats up and emits radiation, infrared light, and that is absorbed, the absorption of terrestrial radiation. This is absorbed primarily by carbon dioxide and water vapor. Those are two really good at absorbing infrared radiation. Then there's the latent heat of condensation. When water evaporates, it consumes energy from the Earth. And when it recondenses to form clouds, it releases that energy into the atmosphere around it. And then lastly, there's just direct conduction from the Earth's surface. The Earth is warm, it's touching the bottom of the atmosphere, it warms that atmosphere up. That last one is the least significant because it really only affects stuff that's right near the surface. And, air is not a great conductor of heat. But that does warm air up and can cause it to rise or sink. Has big effects on weather, but isn't the main way that energy gets transmitted. So just like any other warm body, the Earth will radiate energy. If you get something hot, if anything with a temperature emits light, the higher the temperature, the shorter the wavelength of the light. So the wavelength of the radiation emitted by Earth is inversely related to its temperature, just like everything else. So the Earth primarily radiates energy in the long wavelength infrared region. You primarily radiate energy in a shorter wavelength infrared region because you're at a higher temperature than the Earth. And the main absorbers of that infrared radiation are water vapor and CO2. So these are the primary absorbers of infrared radiation in the atmosphere. There's some interesting tricks you can do where there are these passive cooling paints that emit infrared radiation at a place where there's a gap in absorption. So they, when you heat them up, they primarily they have other properties that cause them to, primarily emit infrared radiation in this one gap, not the normal way you emit radiation. But this basically allows that energy to escape. It can have some interesting side effects. So water vapor and CO2 are the main absorbers of infrared radiation in the atmosphere. This absorbed energy heats the lower atmosphere and helps to maintain the Earth's average temperature. This is what's known as the greenhouse effect. And it's a good thing that there's some greenhouse effect, because if there was no greenhouse effect, it would be a frozen ball like Mars. But we don't want too much, because then we'd be a horrible hellscape like Venus. So this is the greenhouse effect, where visible sunlight comes in, it's absorbed, it's re-emitted as infrared radiation, and it's selectively absorbed by various atmospheric gases. And it's usually compared to a greenhouse because glass will absorb infrared radiation. It's not the most accurate example because actually greenhouses don't stay warm primarily from the fact that they don't let out infrared radiation. There's other effects that is the reason they stay warm, but here is a short video about the greenhouse effect and greenhouse gases emitted by various processes, and why we have a problem that the greenhouse effect is increasing. Yes.
The greenhouse effect is a natural phenomenon. Sunlight falls through the atmosphere to the Earth, heating its surface. Not all of the heat remains there, however. Most of it is emitted as long-wave thermal radiation from the Earth's surface into space. In this respect, the gases in the Earth's atmosphere play an important role. For the most part, they allow the short-wave solar radiation through, but the long-wave thermal radiation which is coming from the surface is partly absorbed by these gases, which means that additional heat is stored in the atmosphere, like in a greenhouse. As a result of human activity, more and more of these greenhouse gases are finding their way into the atmosphere, strengthening the greenhouse effect. The additional heat is causing climate change, with the Earth literally heating up, and with some huge consequences for the environment and people. Carbon dioxide has by far the greatest share of anthropogenic greenhouse gas emissions, which means emissions that are caused by human activity. This mainly arises when fossil fuels such as coal, crude oil or natural gas are burned. To be able to better summarize and analyze the effects of these gases, their global warming potential can be expressed in the form of CO2 equivalents. This shows how much more an individual greenhouse gas contributes to global warming in the next 100 years, compared with the impact of CO2. Accordingly, the impact of methane is 25 times greater than CO2. Therefore, in the first 100 years of its emission, 1 kilogram of methane contributes 25 times more to the greenhouse effect than 1 kilogram of CO2. In Germany, methane largely arises through agricultural livestock farming and the waste sector. The impact of nitrous oxide is 298 times greater than CO2. This mainly arises during the production and use of fertilizers and in the chemical industry. Although fluorinated gases only account for a very small proportion of total emissions, some of them have an extremely potent greenhouse impact. The CO2 equivalent of sulfur hexafluoride, for example, is 22,800. F gases are used as coolants and extinguishing agents, as propellants and in solvents, among others. In Germany, most greenhouse gas emissions arise when fossil fuels such as oil or coal are burned to generate energy. The primary source in this area is the energy industry, for example, the generation of electrical power and heat. This is followed by transport, industrial furnaces, private households, and the commercial, retail and service sectors. Other emissions are caused by the production processes in industry, agriculture, and waste management. If emissions from energy production are broken down and the share accounted for by industrial furnaces and production processes are added together, it is clear that industry, as a whole, is the second biggest source of emissions. All of these emissions intensify the greenhouse effect. For this reason, it is necessary to reduce the emissions of greenhouse gases as far as possible, or, ideally, for them to be stopped entirely. Important political measures include a transport revolution, for example, more walking, cycling and use of public transport, a switch to electromobility and, overall, significantly fewer cars and lorries on the roads. More efficient and more economical fertilization and lower livestock numbers in the area of agriculture. And of course the energy revolution, i.e. the complete phase-out of coal-fired power generation in favour of renewable energies and the efficient and economical use of energy. Fewer man-made gases mean less warming, and every reduction in emissions makes an important contribution to the protection of the climate.
So, another factor that transfers heat to the atmosphere is the latent heat of condensation. So a large amount of evaporation occurs globally due to the insolation that reaches the surface. But it takes a lot of energy to convert water from liquid to gas, which is what you're doing when you evaporate something. It requires 540 kilocalories of heat to change 1 kilogram of water into vapor. So that energy gets stored in the fact that the water turns into a gas. So enormous quantities of latent heat are transferred into the atmosphere when that water converts back into a liquid, when it condenses. These are released during the condensation of gaseous water into things like clouds, fog, rain, dew, etc. So when you turn a liquid into a gas, it requires energy. So that releases energy. You as a human being are designed to exploit this fact. This is why we sweat. We use the evaporation of water on our skin to pull heat from our body to cool our bodies down. And then when that recondenses somewhere, it releases energy. And so when something, when water condenses on a surface, it warms that surface. So that's the latent heat of condensation. And when water condenses in the atmosphere, because it gets cold enough to turn back into water or to freeze from water vapor and form clouds, that energy is released. And there's a similar latent heat for freezing as well. So there's energy released when something is freezes. And if you've ever used a reusable heat pack, that actually exploits this fact. And then there's conduction from the Earth's surface. There's also a significant amount of heat that's just directly conducted from the surface of the Earth into the atmosphere. Now, air is not a very good conductor, which is why we use trapped air as an insulator to keep things warm or cold. So this process is really only effective in the lowermost atmosphere where air is directly contacting the Earth. And due to this phenomena, the temperature of the air tends to be warmer near the surface of the Earth and decreases systematically with altitude. So all of these basically, the release of radiation and the direct heating from the surface of the Earth warms from the bottom of the atmosphere. And that's, now if you want to study the atmosphere and weather and things, there's a few things you need to be able to make measurements and observe. So in order to study and understand the atmosphere's properties and its characteristics, you need to take certain measurements. These include pressure. You want to know how much atmosphere is there. That's roughly what you're measuring with pressure. You're actually measuring how much the atmosphere is squeezed, but it does correspond to density. And it has a bunch of relation. It relates to how wind flows and a lot to do with weather. So you use a barometer to measure pressure. One right here. As we can see now that this barometer is garbage. I think it's broken. Because the reading it has right now doesn't match the weather outside, which makes me think there's something wrong with it. We can also measure humidity levels. How much water is in the air? We can measure the dew point, which is another way to talk about how much water is in the air. They're related. The dew point is the temperature at which, when you cool the air down to, water will start to condense. The wind speed and direction, that's useful if you want to understand how air is moving around. And lastly, precipitation. Is it raining and how much is it raining? So like right now, it's raining. And there's precipitation. That's why I thought the barometer reading was odd. Because generally low pressure corresponds to cruddy weather. So pressure is force per unit area. It's force over area. And at the Earth's surface, we experience the weight of all the atmosphere above us. And this is significant. Every square inch of your body is experiencing 14.7 pounds of force from the atmosphere above you. That is atmospheric pressure, 14.7 pounds per square inch, or what is it, 1.013 bar, or 1.013 times 10 to the 5 pascals. That's pressure. And that's a real thing. There's air pressure and gravity. I think I can do this demo.
Hi, I'm Jared, and I'm back for another experiment on air pressure. Again, this is going to be with lesson number 3. Very simple materials again, very user-friendly. So we have a very simple beaker here. It has a very smooth top, easy to find anywhere, and I filled it with water and red food coloring. Red, green, yellow, you don't even really need the food coloring. In fact, I probably wouldn't put it in because it could stain if it does leak. So I filled it with the water. And what I'm going to do is I'm going to place a card. This is a very simple index card. If you wanted to run this through the laminator to have some lamination on it, That way you could use it again and again and again from year to year. This was actually off a calendar. Very simple. So I'm just going to start with an index card, 3 by 5. And all I'm going to do is I'm going to be placing this index card on top of the beaker and then flipping it upside down. And you would expect the weight of the water to just push that card off of that beaker, spill all over the table, spill all over my lap, and I don't want to get my clothes dirty, so we're going to try this scientifically. We said air has pressure, and we want kids to see that pressure pushing, holding, all that great stuff. So here's how we're going to do this. Here's the beaker. We're going to put the card on top. I'm going to hold the card with my hand, flip it, and now hold the beaker. You can see the card stays in place. Amazing, amazing, amazing. So why? Why is that happening? Well, we have air in this room pushing that card in place. And this is actually, there's a nice tight seal formed on this index card. The water is forming a nice seal, and that seal does not allow air into that beaker. If I were to just tilt the corner and allow air into that beaker, and what will happen if I keep this here long enough, air will actually be able to get through the paper as it gets wet, and I'll lose my seal. But you can see the air pushing and holding this card in place. Why? Air has pressure. It's so easy to do.
So just to show he wasn't faking, this, you need a nice smooth rim so there aren't any leaks, so you get a good seal. And this is gonna fail pretty soon, actually. So the moment it leaks, well, air can get in and it can fall out. So if we want to measure the air pressure, well, as you can see, the air provides a force upwards. So, well, you can just have a tube and see how much stuff air could push up. But you don't want to do that with water because it turns out the tube would need to be like really tall, several stories, like 6 stories tall or something. It's like 100 meters. It's ridiculously tall. But so this was invented by Torricelli after Galileo did some work with the columns of water. So what you have is a column of mercury that is supported by the weight of the atmosphere on the surface of the reservoir of mercury. And you use mercury because mercury is a dense liquid, 13.5 times denser than water. So you don't, but this requires 30 inches of height, or 76 centimeters. So, if you did it with water, you need 100 meters. Or some, wait, no, that's not right. You need 10 meters. I converted wrong. But that's like 3 stories. Yeah, it would need to be like 30 feet. A little bit less than 30 feet. No, a little bit more than 30 feet doing conversions. But it's tall. So I got the numbers wrong because I can never remember them. But yeah, it's a 76 centimeter column. This is 30 inches. That's a little more than 2 feet tall. And the column of mercury gets supported by the weight of the atmosphere on the surface of the reservoir of mercury, and therefore the height of the column of mercury depends on atmospheric pressure. And one standard atmospheric pressure will support 76 centimeters of mercury. Now this is awkward because it's a 2 foot tall, it's a 30-inch tall, more than 30-inch long tube of liquid mercury that's exposed to the atmosphere. It's just an awkward thing to deal with. I mean, and it's not the safest thing because mercury isn't the greatest thing to work with. Not so bad if it's just liquid mercury. Liquid mercury is a lot safer than mercury compounds, but just not something you want to deal with. So if you want to make something more compact, you have something like this. which has a small chamber in it that is compressed or expands. It's a sealed chamber. It gets smaller or bigger as the atmospheric pressure changes, and that's coupled to the needle. So the needle will move. Now, unfortunately, pressure is one of those things that has way too many units because it was measured in things like how tall is my mercury column. So the SI unit is for atmospheric pressure. One atmospheric pressure can be expressed in a number of different ways. The SI unit is 1.013 times 10 to the 5th newtons per meter squared, or pascals. The British unit is 14.7 pounds per square inch. But pressure also has some systems based off of how tall your column of mercury is. So it's 76 centimeters or 760 millimeters of mercury, or 30 inches of mercury. If you look up pressure in the US, you'll get inches of mercury pretty commonly. Or it'll be measured in torr. Torr is another name for a millimeter of mercury. And pressure gauges can be in any of these units. Or bars. So 1013 millibars, where bar is a old unit from the CGS units that happens to be very close to 1 atmosphere, which makes it super convenient. So 1 bar is 10 to the 5th newtons per meter squared. So 1.013 bar is 1 atmosphere. And so bar is commonly used because it's a nice round number in SI units, and it's close, it's approximately 1 atmosphere. But it is an old unit from the CGS system that was a system based on centimeters, grams, and seconds that used to be used. And an aneroid barometer, like the one on the wall over here. So due to the danger and awkwardness of handling a column of mercury, another type of barometer was developed. This is called an aneroid barometer. This is a mechanical device having a sealed metal diaphragm that's sensitive to pressure. So fair weather is generally associated with a high barometric pressure. Rainy weather is generally associated with a low barometric pressure. And if you work with stuff with pressures, the gauges can come in any of those pressure units. It was a big pain in the butt when I was doing my research, because it was like some things were in torr, some things were in bar, some things were, and you had to be able to convert. So in general, nice weather is associated with high pressure, rainy weather is associated with low pressure. And I think this barometer is messed up because it's currently showing quite high pressure, and it's raining outside. And these aneroid barometers, they can be quite small. They can fit them on basically a chip now. So you can have a pressure sensor that you can put in your pocket. So another thing is, oh, we're just about out of time, but humidity is the measure of water vapor in the air. And we can talk about absolute humidity, which is the actual amount of water vapor in a given volume of air. So in the US, absolute humidity is commonly measured in grains per cubic feet. In the rest of the world, it's measured in grams per cubic meter. And the most common method of expressing water vapor content in the air, however, is in terms of relative humidity. Relative humidity is a measure of how full the air is of water. It's the ratio of how much water is in the air to the maximum amount of water the air can hold. So if the humidity is 50%, the air has got half of its capacity filled. And that means air with the same amount of water in it will change its relative humidity if you change the amount of water it can hold, generally by changing the temperature. So if you take a lump of air, seal it in a box so no water can escape or enter, and if you lower the temperature, its relative humidity will increase because the amount of water the air can hold will decrease. So relative humidity is the ratio of actual moisture content to the maximum moisture content capacity of a volume of air at a given temperature. So, and relative humidity is how full of moisture a volume of air is at a given temperature. Part of the reason we use this is what we feel as humidity, because relative humidity is what affects how easy evaporation is, and that's the main effect from humidity. It affects how easily water evaporates from our body, so how easily we cool. And that's all we're going to do for today. We will continue this next time. You have the Chapter 15 quiz today. Have a nice day. Hmm.